I see one person arriving, so we'll start after she's here.
Okay.
Okay, so let's start now. So Zhan Wang, the floor is yours.
Okay, thank you very much. Thank you very much for inviting me to give a talk in Cambridge. Sorry, I couldn't go to Cambridge. So today I'm going to talk about the moving loads on the ice. So you can imagine the thin elastic sheet on the top of the fluids, and which is deformed by the load, so moving loads. So we try to understand the generation and evolution of these deformations. This is an outline of my talk. First of all, I try to say a few words about the background, and then I would elucidate the relationship between hydroelastic wave and nonlinear Schrödinger equations. And then I try to present some results, previous results in two-dimensional and three-dimensional problems. And then finally, I would like to propose a new model, which is used to capture the local bifurcations, the bifurcation structure near some magic speed. This is a joint work with Professor Paul Milewski from University of Bath and Professor John Mark Vandenbroek from UCL. So before talking about the moving loads on ice, I would like to say a few words about moving loads on a train track. It seems a quite different problem, but actually they're essentially very similar. I try to persuade you that they are essentially similar, at least in the linear sense. So all the aircraft or weapons need to be tested before tested on the ground before we put them into use. So there's two ways to test the aircraft. So the first one is you put an object in a nozzle, in a shock nozzle, and you blow in air onto the object using very fast the wind. So then, because of the relativity of movement, then you can examine the materials and the aerodynamic configurations. And the second method is just to tie the object onto a train track and moving the object using the rocket engine. So then you can gain very fast speed. And the world record is 8.5, Mach 8.5. That means the speed is 8.5 times the local speed of sound. So which was carried out in Holloman Air Force Base in the US. Now the question is the stability of this system. It's a faster train track system. Is that stable if we move the object with a very high speed? So we can then formulate the problem using mathematics, right? Write this problem in using physical laws. It's just the Newton's second law, F equals ma, and using the Euler-Bernoulli beam. So ma is the first law, y the second derivative with respect to time, and you have two restoring forces. The first restoring force, you can imagine that the beam is a sort of it's an elastic beam, and you can have a deformation, elastic bending. So the linear part is just the force derivative of the displacement. And you can also imagine the soil below the beam. You can use this spring. You can imagine them as a lot of springs, and then you can model them using Hooke's law. You can also have inertia and you can also have viscosity and pre-stress or compression. Then the moving load is modeled as a delta function. If then this is just a linear problem, right? It's very easy to solve if you can neglect viscosity and neglect the buckling, pre-stress, and you can try to find a steady solution. You will end using the Fourier transform, and you will end up with the inverse Fourier transform of the red part. So the red part is something interesting because the denominator is very, very interesting. So V is the moving speed of the load. And if V is very small, the denominator is essentially always positive for whatever K is. You can always take the inverse Fourier transform. But when V is large, the denominator could be negative and 0. Then the inverse Fourier transform could be complicated. So there must be a critical V, the smallest V, such that the denominator could be 0. So this is called the critical speed. You can, for example, you take the E, the Young's modulus is 1000, chi is the Hooke's law, the constant is 10, and the density is 1000. And you can calculate, find the critical speed is 360 kilometers per hour, which is a very reasonable speed. A lot of train can achieve this speed. And when the speed is close to this critical speed, then the deformation of the elastic beam could be very large, then the system becomes unstable. Okay, so now let's move on to the problem on the ice sheet. So people knows how to use the ice sheet as a transport link for very long history, has a long history for a very long time. So this is a picture extracted from Squaw's famous book in 1996, The Emperor of China on the Move in Beijing, held by a team of 8 people. And there's also a lot of man-made floating structures. The most famous one was made in Japan, the Mega Float structure. It's an airport, floating airport, and it's about 100 kilometers in width and several 1 kilometers in width and several kilometers in the length. And this sort of man-made structure was made in 1998 to 2000. It was tested and had been proved to be workable. So the floating airport is a sort of environmentally friendly system because it has less impact on environment than the land-based alternative, and is self-sustaining system because it can convert ocean waves into energy for the airport. And if you Google on the internet, if you Google the words ice road truckers, you will find a very famous TV show all around the world. It's produced by the Canadian people. So over the past several years, it demonstrates the use of frozen river and the sea as roads in the Canadian and Alaskan Arctic during the winter, of moving very heavy loads by truck. And you will find that in the program, that in the TV show, that you have to drive the truck very carefully. If you don't drive carefully, then you will break the ice. So the left picture is a typical example of ice breaking. And the right picture is even more interesting because there's a speed limit sign. So it tells you if you want to drive a truck on the ice, then the speed of your truck should be between 10 to 25 kilometers per hour or 40 to 70 kilometers per hour. You are not allowed to drive your truck from 25 to 40 kilometers per hour, which is very strange because you have some limitations in between, in the middle. So people try to understand why that happens. Right? As some other background, some military purpose. So in 1950s, Antarctic exploration, mostly of military interest, start to rely heavily on aircraft landing on floating ice sheets because you have to transport the people to the polar regime if you want to explore something, right? And then you need to use some floating, very large floating ice as a transport link as the airport. So people start to examine whether we can do that. Is that safe? So in 1958, so a person called Wilson at the University of Michigan as a researcher, and he conducted a lot of experiments and observations. And he, about the aircraft landing, he measures the displacement of the deflection of the ice sheet for the aircraft landing and takeoff and the constant moving with constant speed. So in 1958, he published his report. And he found that in the report, he said a localized, stable, large responses are generated as the plane moving close to the certain speed. And in the report, he said, all the takeoff records show the order double characteristic of the one shown in figure 14. So the right figure is a figure 14. So second wave cannot be a reflection. And the middle figure is in figure 14 is the takeoff record. So the second wave there's two waves in the figure. The second wave cannot be a reflection from the show as it arrives much too early. So most logical explanation is as follows. He said, as the plane starts its takeoff run, it gains speed rapidly and passes through C mean, generating a large wave, which then falls behind the first wave that accompanies the plane. So he found the two waves in the takeoff record. One wave is just the forced by the plane, and the other wave comes from nowhere. And he explains that why does that happen? That's because there's a magic speed, which is called the C mean, when the aircraft moving with the speed of pass through C mean, then energy is enough to generate a large response. So that's the explanation. So people, because it's a very interesting phenomenon, there's some critical speed in the system, then people try to understand more about this problem. So in 1980s, a lot of experiments has been carried out in 1980s, and the two famous ones are one is in the McMurdo Sound in Antarctic, carried out by the group of Sled in 1988, and another one is the other one is in Lake Solomon in Hokkaido in Japan in 1985, 87, and 88. So these two experiments are different because one is the McMurdo Sound is in deep water scenario, and in Lake Solomon is in shallow water scenario. In deep water scenario, the thickness of the ice is 1.6 meters, and the water depth is 350 meters, and the critical speed is 18 meters per second. And in Lake Solomon, the thickness of the ice is 0.17 meters, and the thickness of the water is 6.8. So the water depth is 6.8 meters, and the critical speed is 6.1 meters per second. So when the load moving close to the face, close to the critical speed, the amplitude becomes very large. If it away from the critical speed, the amplitude drops very quickly, reduces very quickly. So that's the phenomenon they observe. And this figure shows the experiment in McMurdo Sound, and this figure shows the experiment in shallow water in Lake Solomon. And you can see the right figure shows that the critical speed is about 6, and close to 6, the amplitude of the deflection of the ice sheet become very large, and away from 6, the amplitude is okay. And if we focus on the wave profiles of the deformation of the ice sheet, and if the speed is close to the critical speed, then the solution looks like a solitary pulse in the middle with oscillatory decaying tails on both sides. We try to mathematically formulate this phenomenon to understand from mathematical point of view. So the problem is quite easy to formulate. It's just we can assume the flow is irrotational and the fluid incompressible and inviscid and incompressible. And the governing equation is just a Laplace equation, potential theory, and there are two boundary conditions, a kinematic boundary condition, a dynamic boundary condition. There are two restoring forces in the dynamic boundary condition. One is the gravity, another one is due to elasticity, bending. And we use the simplest nonlinear elastic model, the Kirchhoff-Love model, is just the second derivative of the curvature. This is a widely used elastic model. And so first of all, we try to understand it from the linear point of view. If we can say something more about nonlinear results. So the linear problem is quite easy to solve. For simplicity, we assume the fluid is of infinite depth, and the pressure is a moving load. The pressure is just a delta function translating with a constant speed. And we neglect all the nonlinear terms and using the Fourier transform to solve the problem, try to find the steady state. And the result, it end up with the integral of it's just the inverse of Fourier transform, which is very similar to the moving loads on the train track, because the denominator, if we focus on the denominator, if the speed of the moving load is small, and the denominator is always essentially positive, and you can take the inverse of Fourier transform. If u is larger than the denominator could be 0 and negative, there must be a minima u such that the denominator becomes 0 at some wave number k mean. So the critical wave number is k mean, and the critical wave speed is c mean. Then if we take the speed which is slightly below this critical speed, very close to c mean, but slightly below c mean, then you can make sure the denominator is positive, and you can take the Fourier inverse transform, and we use the residue theorem. You will end up with the solution as an expression of the solution. So a lot of interesting phenomena in this expression. Number one, the solution consists of a carrier wave, it's a sinusoidal wave, and an envelope, exponential decay envelope. That's number one. Number two, the carrier wave, the speed of the carrier wave, the speed of the envelope, and the speed of the load are all the same. They all propagate with the constant speed of u. And number three, the envelope is much longer than the wavelength of the carrier wave, because u is very close to c mean. So this in the exponential, this is a small parameter. So the envelope is very long. Number four, if u is very close to c mean, the amplitude could be very large in this expression. Okay, so that means, what does that mean? That means because at this particular point, c mean, the group velocity, which is a propagating velocity of the envelope, and the phase velocity, the propagating speed of the carrier wave, are the same, and they also equal to the speed of the load. So the energy cannot propagate relative to the load, because the envelope is the speed of the group velocity is the propagating speed of the energy, so cannot propagate relative to the load. And then the energy will accumulate with a very small regime, with a very fully localized regime. As the energy accumulates, the amplitude increases. As the amplitude increases, it reaches a certain level, then the linear approximation breaks down. Because the linear approximation, if you want to make a linear approximation, the amplitude should be small. Then when amplitude becomes large, the linear theory doesn't work. You have to include some nonlinear terms to suppress the unlimited growth of the amplitude. So that's why we try to add some nonlinearity in the system. Okay, now let's move on to the nonlinear theory. So we first do the weakly nonlinear theory. So we try to understand the dynamics of the envelope. Then we take, motivated by the results in the linear theory. So the solution looks like a carrier wave multiplied by an envelope, a very long envelope. So we take a sinusoidal wave and multiply by a slow varying small amplitude envelope. And then you substitute the answers into the hydroelastic wave problem that you're going to solve, and you can do you can expand about the small parameter epsilon. This is a sort of multi-scale analysis, right? And finally, you will end up with the equation governing the dynamics of the envelope, which is the nonlinear Schrödinger equation. As there are two constants in the nonlinear Schrödinger equation, which one is just the dispersive coefficient, and the mu is the Stokes nonlinearity. And the Stokes nonlinearity changes the frequency in the mean field approximation. And the specific values of lambda and mu are not very important, but the combination of these two constants is important. So if lambda times mu is negative, then this NLS is called the focusing NLS, and the system is in the Benjamin Freire unstable regime. And you can expect you will have a solution decay to zero in the far field. You have bright soliton solutions. And if lambda times mu is negative, then is a positive, then NLS is called the defocusing NLS. You are not supposed to have solution decay to zero in the far field. You are supposed to have solution called the dark soliton, which approaches infinity, approaches a constant state in the far field, non-zero constant state, and decay to zero in the middle. So if you want to see some solution in the experiment, some solution pulse in the middle and oscillatory decaying tails in the far field, you are supposed to have you need the two conditions. One is you need some solution, you need some non-dispersive point where the group velocity equals the phase velocity, and the second is the envelope should be of defocusing types, and the last should be focusing type. Then you can have solution decay to zero in the far field. So that's two conditions for the existence of Wavepacket solitary waves. And in 2002, Palou and Diaz studied the fractional gravity wave problem from a weakly nonlinear theory. And they find that there is a critical depth, HC, above which the analysis coefficient are focusing type, and the Wavepacket solitary bifurcated form infinitesimal periodic waves. That means they found that in shallow water, the analysis is a focus, and you can expect the Wavepacket solitary waves as observed by the Japanese group in Lake Solomon. But in deep water, the analysis is defocusing. We are not allowed to have small amplitude Wavepacket solitary waves. So their result shows that if in deep water situation is very complicated, it's not, the weakly nonlinear theory doesn't work. But if you go to the McMurdo, the experiment in McMurdo Sound, we do observe some Wavepacket solitary waves. So that means the weakly nonlinear theory doesn't work. We cannot use the weakly nonlinear theory to explain the experimental phenomena that observed in deep water by the New Zealand group. So we have to go back to the primitive equations, to the full Euler equations, to see whether we can find the solution in the full Euler equations to the fully nonlinear problems. The weakly nonlinear problems is not going to work. So now we try to solve this problem with the fully nonlinear problems, the fully nonlinear equations. So we solve the Euler equations, and there are a lot of numerical scheme, very good numerical scheme for two-dimensional water wave problems, and most of them based on the conformal map technique, because the conformal map can keep the Laplace operator and maps the irregular domain to a regular domain. Then you can solve the Laplace equation in the regular domain analytically. Then you all the variables on the free surface, only these variables need to be considered. So that means you reduce the dimension of the problem by one. So the two-dimensional problem becomes a one-dimensional problem. Then you can, I don't want to go to details, a lot of people know that. So okay, so if you want to find the traveling waves, the scheme is even simpler because it just becomes a one single equation. I try to spend 2 slides to describe the results that we obtain. So the key problem for this, the crucial to this problem is not to the forced problem. So the problem is with forcing, right? So we don't need to worry about the forced problem. We only need to about the free problem. So we first consider the problem without forcing. Then the question is, can we find the Wavepacket solitary waves without forcing? Just the problem without forcing. If we can find solitary waves, Wavepacket solitary wave without forcing, then then we can go back to add the forcing to the system. And the forced solution is just a small perturbation of the solution without forcing. Okay, so that's the first step, is to find the solution without forcing. So the answer is yes, we can find large amplitude solitary wave-packed solitary waves without forcing. And this solution can only exist at finite amplitude, cannot exist at small amplitude. And the bifurcation structure of the problem is very, very difficult. It's very, very different from other problems. It doesn't bifurcate from 0 amplitude. It bifurcates from, it appears along the branch of the generalized solitary waves. So the B is the generalized solitary, which is a solitary pulse in the middle with non-decaying oscillator tails in the far field. And it appears along the branch of generalized solitary waves, and the generalized solitary waves bifurcated from periodic waves. So that's the bifurcation structure for this problem, for the hydroelastic wave problem in deep water. And then we add the forcing to the system. So what's going to happen? So everyone knows that if people working on nonlinear waves knows, if we apply forcing if you had a boat and moving the boat on the shallow water, then you will see the generation, a periodic shedding of solitons upstream. So this is a very interesting phenomena, but people know that. So for pure gravity wave in shallow water, if we apply a boat and moving the boat with a constant speed, what's going to happen? So without boat, for pure gravity waves, so there is also a critical speed, which is square root gh, which is normalized to unity in this figure, in the figure on the right, and all the linear solution existed below this critical speed, square root gh, and the solitary waves exist above square root gh. Now you add forcing to the system, and you try to find the steady state, and you will find the blue dashed curve exists upstream, exists supercritical. So because you add forcing, then you break the symmetry of the bifurcation. You have two branches of the solution. One branch is a small perturbation of the free solitary waves without forcing, and another branch, the lower branch, is a small perturbation of the free stream. And the interesting thing is there is a gap between the forced solution, as a steady forced solution, and the bifurcation point, square root gh, which is called the transcritical regime. And if you use the boat and moving the boat with the speed in the transcritical regime, you will never reach the steady state because all the steady solutions on the right. And because in the transcritical regime is very close to the critical speed, whereas the group velocity is equal to the phase velocity, if you apply forcing with the speed in this transcritical regime, you have no linear mechanism to radiate energy. Then the energy accumulates in this transcritical regime, and as the energy increases, the amplitude increases, and the amplitude reaches a certain level. The small dispersion and the small nonlinearity will make a subtle balance, which results in the formation of soliton, KdV type solitons. Then this soliton propagates slightly faster than the moving boat. Then it grows and propagates away. This is a sort of nonlinear mechanism to radiate energy. And our problem is different. So because the bifurcation mechanism for the free problem is very different. So the red curve is the solution without forcing. So first you have periodic waves up in the supercritical regime. Then you have a bifurcation point which leads to the generalized solitary waves, a turning point that leads to the generalized solitary waves, and you further decrease the speed, which passes through the bifurcation curve. Bifurcation point, then the amplitude of the tail decay to 0. So you will have bright soliton solution. And now if you add a forcing to the system, our problem is very much different from the shallow water case, because if you add a small forcing to the system, then you will not find this transcritical regime, because the small forcing solution fulfills the subcritical regime. But if you add a larger forcing, a considerable larger forcing to the system, then you will have a transcritical regime between the steady solution and the bifurcation point. So if you apply the considerable larger forcing with the speed in the transcritical regime, you will not have linear mechanism to radiate energy because all the linear waves on the right, and you will never reach the steady state because the steady state is on the left. And the only solution exists in the transcritical regime is the bright solitary wave solution. So what you see is you will see the periodic shedding of bright solitary waves with complicated motions, transient behavior. So, that's the explanation for what was observed by Wilson and Squires. So, so we can do the direct numerical simulation. We can apply larger force into the system. You will see a large deflection generated by the forcing, and which is this structure is stable, can propagate it with a long distance, and sometimes it will break the ice. And if you apply small forcing, the right-hand side, small forcing, then you will see just the small ripples. We'll never see a large amplitude diffractions. So that means if you want to safely use the ice sheet as a transport link, you have to stay away from the critical speed. Okay, so the next question is, can we find dark solitary waves? Because analyzing deep water is defocusing, then which predicts the existence of dark solitary waves. The answer is yes, we can find dark solitary waves in the full Euler equations. And the dark solitary wave bifurcated from infinitesimal periodic waves, then it exists in the supercritical regime, and then it also features a turning point. After turning point, the solution becomes generalized solitary waves until it reaches the bifurcation point. After that, it becomes a bright soliton. But the solution is multi-packet. It's different from the bright soliton solution that we explored in the previous several slides. So it features two depression waves sit side by side. So that's the bifurcation for dark solitary waves. We'll go back to this problem later on. So we choose a model which has been widely used, but there's no clear conservation. So we use a Kirchhoff-Love model for the elastic beam. So the second derivative of the curvature. And this is there's no clear conservation form for the elastic potential energy for this model. But then in 2006, Toland proposed a conservative model for the nonlinear elasticity portion of this problem using the special crossset theory. So in this case, the pressure is the energy is just the curvature square. So it is very understandable, right? So because the energy should be independent of coordinates, should be some geometric quantity, and then if you take the variational derivative of the energy, there should be the force derivative of the displacement. So, and then the energy should be positive. So the simplest one is the curvature square. And for this new model, you can also take the normal form analysis. You try to find the nonlinear Schrödinger equation for this problem. If you in the Toland's model, with the Toland's model, the analysis is also defocusing shallow water. It's also defocusing. You have to go back to the primitive equations to explain that the phenomena that you observed in the experiment. You are not allowed to use the weakly nonlinear theory because NLS doesn't tell you there's take a Wavepacket solitary waves. Okay, so try to spend a few words about the three-dimensional problem. So this is a radar satellite's measurement ice cover displacement induced by moving load. You will see the structure is quite fully localized. You will see a red spots is the position of cars, and the waves are quite fully localized. So it's like a lump solution. So the question is, how can we model three-dimensional problems? Is that possible to find the lump solutions in these problems? Are they stable, and how to generate these lump solutions? So So first we have to generalize the two-dimensional problems, a model of two-dimensional problem to three-dimensional, and which was done by Toland and Plotnikov in 2011. They used the celebrated Helfrich Hamiltonian or Wilmot functional. It's just as a combination of the mean curvature square and the Gauss curvature. And the Gauss curvature could be neglected because of if the plane asymptotic approaches the horizontal plane or is periodic on R2, then the Gauss curvature should be neglected because the total Gauss curvature is constant. And it has no contribution when you take a variational derivative. And you can write down the Hamiltonian, the energy, total energy for the whole problem, which is the kinetic energy plus the potential energy due to gravity and the potential energy due to elastic bending. And then you take a variational derivative using the canonical variables, the surface displacement theta and the velocity potential on the free surface phi. So there's a canonical equation for the Hamiltonian system. And then you can also do the normal form analysis. You can try to find the nonlinear Schrödinger equation. However, it's not a nonlinear Schrödinger equation in finite depth. In finite depth, it's a Benney-Roski-Davis-Watson system. It's a generalization of nonlinear Schrödinger equation. Now you have two modulation directions, x and y. And the property of this system is pretty much similar like the nonlinear Schrödinger equation. Also have focusing and defocusing types. In deep order, the system is also defocusing. So you cannot expect lump solution. You have to go back to the full Euler equation if you want to explain the observation of the satellite. So the results shown in the satellite images. So you can compute the full Euler equations. One way is to solve the Zakharov equation because G is called the Dirichlet-Neumann operator, which maps the boundary condition to the Neumann boundary condition. And this operator is an analytical operator if under some conditions. If eta is not very large and the slope of eta is also not very large. And then that means the Taylor series of the operator converges, and then you can expand this operator and you reduce the dimension of the problem. So the three-dimensional problem reduces to the two-dimensional problem, and then you can easily solve this problem numerically. And you can find solutions. You can find lump solutions that observed with the satellite image. And some lumps are stable and some lumps are not stable. I do not have enough time to go to the details, but I'll show you some results. So, and then this problem tells us if we want to safely use the ice sheet as a transport link, you have to stay away from the critical speed. But however, sometimes you try to quickly break the ice. Then you can use the method called the resonance method of ice destruction. If you Google on the internet, you go to Wikipedia, there's an item called the resonance method of ice destruction. And that means you're moving the vehicle on the ice or you travel beneath the ice using submarine. And the moving speed is very close to the critical speed. Then you can quickly break the ice. That's because you concentrate energy with one point, with a very fully localized regime, and you don't waste any energy. So it's a very good way to break the ice if you want. Okay, so there's still a few minutes, and I try to say a few words of this strange bifurcation. So this strange bifurcation, so you have periodic wave, and then you have generalized oscillating wave, and then you have Bryce oscillating wave. So first to go to the supercritical region, then go back to the subcritical region. This bifurcation phenomenon
Hello? Yeah, but I think he's not connecting anymore. Yeah. Hello? He's not back.
So sorry.
Can you hear me? Oh yeah, good. Sorry, we were, there was a power cut, something like that, about 2 minutes ago. Yeah, maybe.
Oh, sorry.
Yeah, maybe we can come back
Very
one or two slides before.
Okay. So this one.
Yeah, we are this one.
Oh.
After this one, we hear you, and then okay.
Okay. Okay.
Thanks.
Good.
And
So
maybe if you can conclude in 3 minutes, will it good for you?
Sure. I will
Thank
do
you.
that. So this bifurcation is very interesting because I've never seen that before. And once I found one example and find a lot of examples, I found that this bifurcation appears in other fluid dynamical systems. For example, this is the example that is a capillary gravity between two semi-infinity fluids. So when the density ratio is bigger than 0.283, then you will see this bifurcation structure. So this is an example when the density ratio is 0.4. And we also found this phenomenon in other fluid dynamical system because the capillary gravity waves on the conducting fluid under normal electric field, on the horizontal electric field, and the flexural gravity waves with constant vorticity. And the question is it possible to find the ad hoc models that describe this bifurcation, this new bifurcation? Is it possible to find this simple model? So like nonlinear Schrödinger, but the nonlinear Schrödinger doesn't work anymore, right? Because it cannot describe the large amplitude solid waves. So the models that we proposed recently is a sort of finite KKP or Whitham or Akers molasses. So sort of models is just as a wave equation add some nonlinearity. So but we have to carefully choose the nonlinearity and carefully do choose the linear part. So the evolution of eta can be factored into left and right going propagating waves. And the full dispersion relation for the problem in deep water is k plus k to the fifth. And because we said there's a right going wave, so there's a sign k. And then you can expand about the minimal phase speed. We focus on this wave number as narrow band approximation, and we expand this about this particular point. And then we write down the linear part. Because we have the dispersion relation, we can write down the linear part of the problem. And the nonlinear part is complicated. How can we choose the nonlinear part of the problem? And in this model, I add a cubic, a quadratic, cubic, and a quartic nonlinearity in the system. Why should I do that? So we choose this model, and we have to. There's two questions: why do we need a quadratic, cubic, and quartic terms? And the second question: how do we determine the coefficient for these these nonlinear terms, the coefficients? And so, first of all, we have a weakly nonlinear dispersive system equation, and we can always derive a Schrödinger equation from this system. This is the universal Schrödinger equation is the universal model, and we can also derive a Schrödinger equation from Euler, and we have to match the coefficients between these two. So that gives you two coefficients, alpha and the beta, and the last gamma is fixed by matching this point. Matching the bifurcation point when for the bright solitary waves at the minimal phase speed. So that's how we fix the coefficients. And we found that the bifurcation structure is very similar to the Euler equations. For the small forcing, there's no gap transcritical regime, and for the larger forcing, you have transcritical regime. And the bifurcation, near the bifurcation point, there's rich with bright solitary, generalized solitary, dark solitary, and multi-packed solitary waves. And we can also generalize this model to 3 dimensions. You will find the lump solution and the generalized lump solutions. And this is the end of my talk. I think I finished on time. Okay, thanks.
Thank you very much. We have time for a few questions.
Thank you for very nice presentation. My name is Korobkin. I have several questions, but first, the most important one. It seems that you are saying that your type of bifurcation is different from bifurcation known in, say, bifurcation theory. And in that theory, we can explain what's happening by using surfaces. So they're similar to theory of catastrophe. And the horizontal plane in your problem is amplitude of the load and velocity of the load, and the vertical axis is the response of the system. And as I understood before your presentation, anything in physics can be explained by a certain surface in this three-dimensional space. Okay, this space could be with higher dimension, but the swallowtail, butterfly, Whitney surfaces, they are there. But and always, if you move on the plane of parameter, you can find different conditions. So always it's continuous. But you are saying in some sense, in your problems, the connection, or not connection, but the some solutions, they cannot be obtained from linear theory. So this is a little bit confusing. So are you saying that you discovered new bifurcation theory?
No, I didn't say I discovered some new bifurcation theory. That means for whatever you use, so like a KdV equation, there's a solitary wave is bifurcated from 0 amplitude, right? So I'll show you. So for example, on the right hand side, so solitary wave is bifurcated from 0 amplitude when at the speed is 12 gh. And then grows, the amplitude increases when the speed increases. But our problem is very weird. So it's very highly nonlinear. So in small amplitude, you are not supposed to have solitary waves. The solitary waves doesn't bifurcate from 0 amplitude. It appears along the branch of generalized solitary waves. And the generalized solitary waves bifurcate from periodic waves. I didn't mean I found some new bifurcation theory. I just mean that it's very different from the existing bifurcation structure in fluid dynamics. Like capillary gravity waves in deep water, then the analyses also the Wavepacket solitary wave also bifurcated from 0 amplitude. So they can exist with small amplitude. But for this particular problem, the solitude cannot exist with a small amplitude.
Thank you. Maybe time for a last question. Then I have a small one that maybe you mentioned the 3D case, and my feeling about 3D is that you have to go from the Euler binary equation to some kind of a Foepel-von Karman equations, which is not the one you consider. Is there any reason for that?
Yeah, you can do that. You can do that. But the amplitude is a bit larger than so there's some limitations for expand the Dirichlet to Neumann operators. The amplitude shouldn't be very large. If you use the linear Euler Bernoulli bin the Laplacian square, and then the amplitude is a bit larger. This numerical screen cannot capture the results. So I use quite a nonlinear model in this problem. Yeah. And you can always do that. You can always use the linear elastic model that yesterday Olga shows that. She can compute this with for Euler. Yeah.
Okay. Thank you very much. I think we can stop for the questions. Thank you again.
Thank you.
Can you stop sharing your screen
so
that the next speaker can